We are presenting our project titled Real-Time Sign Language Translation System, Bridging Communication Barriers Using Cloud Computing and Real-Time Event Processing. Our project focuses on improving accessibility for hearing impaired individuals using scalable cloud technologies and real-time processing pipelines. I am Binu, along with my teammates Harinandan G, Jacob Isaac, and Nived NaIR from the Department of Computer Science. Communication is something most of us take for granted until we realize millions of people experience barriers every single day. This project is an attempt to reduce the gap using technology. Sign language is a visual method of communication that uses hand gestures, facial expressions, and body movements. According to global statistics, more than 466 million people worldwide are having impaired. Despite advancements in technology, communication challenges still exist in classrooms, workplace, hospitals, and public services. Current systems face four major limitations. First, many systems are not real time and suffer from high latency. Second, they are difficult to scale for large number of users. Third, communication still heavily depends on human interpreters. Finally, most systems are not cloud native and lack distributed event driven architecture. Our project aims to address these limitations. The main objective of our project was to design a cloud native real time translation system. So, the goals we are trying to achieving low latency translation for smooth communication, building scalable infrastructure using Google Cloud Services, creating an AI ready pipeline for future machine learning integration, and finally, improving accessibility and inclusiveness in education and healthcare environments. We didn't just want to build another application. We wanted to design a system architecture that could eventually scale to real world public usage. This slide shows the overall system architecture. The system follows an event-driven cloud architecture using Google Cloud Services. The process starts with user input from the front-end interface. This input is then published as events to Google Cloud PubSub. Cloud Run services subscribe to these events and process them independently. This decoupled design improves scalability and fault tolerance. After processing, sign language tokens are generated and stored in BigQuery for analytics and future improvement. Finally, the corresponding sign language visualization is displayed to the user. One important architecture advantage here is that every component can scale independently without affecting the others. The technology stack powering our system. So for the front end, we have used HTML, CSS, and WebSocket for real-time communication. For backend, we have used Python for APIs and processing logic, and FFmpeg for media-related operations. For the cloud infrastructure, we have used Google PubSub for event messaging, Google Cloud Run for serverless execution, Google BigQuery for scalable analytic storage, and Vertex AI for future machine learning integration. Instead of using a traditional monolithic setup, we intentionally designed the system using modern cloud native microservice principles. Now I hand over to Harinandan G.
Hello, all. I am Harinandan G. So, workflow. This slide explains how the system works step by step. The user enters tests through the frontend. The test is published as an event to Google Cloud PubSub. The Cloud Run microservices process the event in real time. The test is mapped into sign language tokens. Metadata and logos are stored in BigQuery. Finally, the corresponding sign language output is displayed visually. The entire pipeline is designed for low latency and scalability. Now, performance. Our system achieves strong performance metrics. The maximum end-to-end latency is under 500 milliseconds. The architecture supports over 100 components. Reliability is maintained at approximately 99.9% uptime. Some important technical advantage include event-driven communication through PubSub, automatic scaling using Cloud Run, reliable message delivery with retry and ordering mechanisms. One interesting aspect is that even if one service temporarily fails, The message system ensures the events are not lost, making the architecture resilient. Now, implementation. Our current implementation already supports. Our current implementation already supports text input through frontend, cloud-based real-time event processing, visual sign language output generation. However, this is only the beginning. Future enhancement Future enhancement include 3D animated sign language avatars, webcam-based live gesture detection, facial expression recognition, mobile application for Android and iOS, and multilingual sign language support. Our long-term vision is to create something similar to real-time communication assistant that works seamlessly across devices and languages. Now, impact. This project has strong social impact potential. It can help reduce communication inequality and improve accessibility in education, healthcare, public services, and workplaces. By reducing dependency on interpreters, the system can make communication more immediate and accessible. Technology becomes truly meaningful when it improves inclusivity, and that is the core motivation behind this project. Now, SDG alignment and conclusion. Our project aligns with two major sustainable development goals. First, SDG 4, quality education by improving accessibility for hearing impaired students. Second one is SDG 10, reduces inequality by removing communication barriers in society. So, to conclude, our project demonstrates a cloud native real-time sign language translation system using Google Cloud Observe, Cloud Run, BigQuery, and Reactions. The system converts text into visual sign language output while maintaining scalability, reliability, and low latency. Future AI integration will further improve context understanding and intelligent gesture.
So, this is our real-time sign language translation system frontend. It is designed for hearing impaired users who need to communicate. You can see it has a clean interface with a microphone button for speech input and a text box for typing. And the backend is connected to our cloud function endpoint. And the first function we have is type and translate. So let me type something here. And I'll click this translate to sign language button. So as you can see, the system sends these words into our cloud function, which processes it and returns ISL tokens. And you can see these tokens appearing as happy and husband. And below here we have the sentiment analysis also. This is done by our Vertex AI. And finally, the video is presented using a launch pop-up. Here you can see the happy is coming like this. And the next word is here. Now, our second function is speech input. And if I click this, happy Holi. Happy Holi. It has been registered here. And if I click the translate, the exact thing is happening in it. It is sending it as ISL tokens and the video is being displayed as pop-up. Now let me type a longer sentence. And as you can see, multiple ISL tokens are being generated and they are perfectly mapped to the video display. All four of them are being generated here. And as also you can see the sentiment score, which is being generated by our Vertex AI. So this frontend demonstrates how our cloud architecture translates into a real usable accessibility tool. Speech or text goes in, and the tokens and video signs come out, all powered by Google Cloud in real time. This directly addresses our project's goal of bridging communication barriers for hearing impaired individuals, aligning with our social development goals. Now I invite Jacob to explain the backend and the Google Cloud part. Thank you.
Thank you, Nived. Now I hope my screen is visible. Okay, so here, this is our Google Cloud project. Sign lang translation. Here we have used 4 Google Cloud components over here. PubSub, Cloud Functions, BigQuery, and Vertex AI, all running on free tier credits. So let me walk you through each one. So the first one here, we have BigQuery. BigQuery is actually our data warehouse. So this is where our translations are stored here automatically. So now I'll show you a live query right now. So as you can see here, select user ID, input text, sign tokens, and sentimental score and timestamp from this project. So now if I run this, here as you can see, the previous entered just what Nived entered right now. Happy Holi, happy husband, and happy family water cat, which was, and also timestamp is also shown here. And also the sentimental score, sign tokens, and the input text are equally shown here. You can see that from different users, it is shown, and the Vertex AI sentimental score is also shown. So this actually proves that the full pipeline is working from end to end. So this is about the BigQuery. Now I will show you the pub subtopics. This is the Google Cloud PubSub, our event ingestion layer. So when any message is published to this topic, it automatically pushes to our Cloud Function endpoint here. This is the event-driven architecture mentioned in our abstract, asynchronous communication between components. The subscription is configured with a push endpoint pointing directly to our Cloud Function. So the moment the moment event publishes a messages, it reaches here automatically. So this is about the PubSub. And now I will take you to the Cloud Functions. So here, as you can see in Cloud Functions under Services, the sign language translation has been deployed and public access has been provided under the region US Central 1. This is our serverless compute layer. This replaces traditional servers. It receives the text input, converts it into sign language tokens using our ISL mapping dictionary, calls Vertex AI for sentiment analysis, and stores everything in the BigQuery. So here no server management is needed. It scales automatically. So as you can see, I have shown you all 4 components: PubSub, Cloud Functions, BigQuery, and Vertex AI. As you can see in the BigQuery table. So as you can see here, the sentimental score of each and everything is shown over here. Since most of the input text has been happy, the sentimental score has been pointed to 0.9. The sentimental score value lies between -1 and +1. Positive sentences get scores near 1 and negative sentences get score near -1. So for example, in the happy husband section, the sentimental score is 0.9, proving Vertex AI is actively processing every request. So to summarize, our architecture uses all four required GCP components: PubSub for event ingestion, Cloud Functions for serverless processing, BigQuery for storage and analytics, and Vertex AI for intelligent NLP. Everything runs on free tier. So that's it. Thank you everyone for your time and attention. We hope this project demonstrates how cloud computing and real-time clusters can be used not only for technical innovation, but also for building a more inclusive society. Thank you.